What's going on, everybody? This is Mr. Diamond. Welcome to Advanced Chemistry. We are in Chapter 1, Redox Reactions, and we're going to be starting out with our notes. So this is going to be a little bit different if you took organic chemistry. The stuff that we're going to be talking about and the level of the material is going to be a little bit lower, relatively speaking. It's still going to be difficult. It's still chemistry. But we're going to be talking stuff a lot more closely related to general chemistry if you took that with me or at this school. So our first chapter is going to be about redox reactions. And I assume the first question that you have when we get there is what is that? What is a redox reaction? Redox reactions are super important. They are a very, very critical part of basically every type of chemistry that you can possibly do. But let's start at the beginning. As you learned in chemistry and probably some other classes before that, our current understanding is that matter is made up of atoms. Atoms are made out of protons and neutrons. They're in a dense central nucleus, and then there's electrons floating around the outside of it. We call the location that they could be in orbitals. They are not 100% chances. They are clouds of probability. When dealing with reactions, I mentioned way back in general chemistry that one of those particles is usually the most important when dealing with a reaction. And if you think about logically, the neutrons contribute weight, which not that big of a deal. They make something an isotope, which obviously isotopes probably spring to mind things like radiation and radioactive substances, but that's not what we're looking for. Protons determine the type of element that we're dealing with, but other than that, there's some acid-based stuff they do, but they're not super relevant. It's really electrons. Electrons most of the time are the part of an atom that is relevant to a reaction. This is due to the fact that they are moving, they're charged, and for the simplest reason is they're just outside. Like, if you think about, like, currently in my water bottle right here, what is going to be more likely to react with something, this outside layer or the water? Well, even though this is made out of metal, it's not very reactive, and water can be involved in reactions. Currently, that water is not going to get out of there. It's just harder to get to it. I'm going to have to do something to this outer layer first before I can even interact with those. So electrons are kind of the same idea, only instead of it being stainless steel that's not reactive, we're talking about something that's already reactive to begin with. So the electrons are just going to be the thing that reacts most of the time. As we discussed in chemistry, most chemical reactions occur because atoms are trying to gain, lose, or move around their electrons, usually to try to get a full octet. One exception to that is acids and base reactions. They usually involve protons moving around, but those also take place usually in liquids, and there's a couple other things going on with that. But we'll get to that a little bit later on in the class if we have time. In chemistry, we learned there's a lot of different ways to describe atoms. You can talk about electronegativity, ionization energy, atomic radius, charge, isotope symbols, atomic formulas. There is even more than just that, but we're going to focus on a new method that's electron focused. If electrons are the things that really indicate reactions happening, we're going to hone in on those electrons that the atoms have. And instead of just saying number of electrons, we're going to kind of think about reactions in terms of electrons instead of just trying to give them like a number right off the bat. So in some of our previous reaction types, it can be a little bit obvious, not completely, but a little bit obvious as to what's happening electron-wise. And the example we're going to look at here is 2Na plus Cl2 gives 2NaCls. When you look at this, if we were to draw this out, which we'll do in class, if I had a better setup here, I would do my little sketching here, but I cannot, I apologize. You have 2Na plus the Cl2. Those NAs, based on their position on the periodic table, are expected to have a +1 charge. And that's because they currently have one electron that they're trying to get rid of. And the Cls, even though they are kind of in a bond, we could normally think of them as just Cl kind of sitting there separately for the purposes of this reaction at least. The Cls currently have 7. They're covalently bonded to share a pair of them, but they really like to own it. Like, it's kind of the whole, would you rather be like renting a car or own your car? If those are the only two options and everything else is the same, you'd rather own it. You'd rather have the thing. There's not a ton of advantages to like renting the car, renting the vehicle. So the Cls are then going to say, well, we want an extra electron. The Na say, well, we want to get rid of one of our electrons. And they're electron-wise then, the Na has lost an electron to give it to the Cl, and that's caused that bond to break, and that's caused there to be two separate ionic bonds of an Na and a Cl smushed up against each other, connected to one another. For more complex reactions, though, it can get a lot more difficult to visualize what's going on. For example, here, we've got zinc and we've got 2 hydrochloric acid molecules plus zinc chloride plus hydrogen gas. What exactly is happening here? Who's losing and who's gaining? I mean, it looks like this zinc starts alone and ends up bonded to something. Does bonding to something automatically mean it gains or loses? And then the hydrogen leaves the chlorine. The chlorine changes partners. Here there's only 1 chlorine. Here there's 2 chlorines. There's a lot more going on in this. And so just looking at it, it can get a little bit more difficult. So we need to use a new and a different method. And so what we're going to do is we're going to look at these changes in electrons in terms of oxidation and reduction. Those are the terms we use when we assign them oxidation numbers. It's a representation of how the electrons in an element have changed because of a chemical reaction. So first thing to note, and it's going to come up later on here, but we're gonna talk about this in more detail. But number 1, they have to happen at the same time. This is not this thing will get oxidized and there isn't a reduction. If you have oxidation, you have to have reduction. This is a package deal. They're both going to happen at the same time. And then oxidation numbers are not locked in for most elements. There's a couple of them that are, but oxidation numbers have to be determined on a given chemical's basis. And it can change from side of reaction to side of reaction, which is kind of what we're going to look at here. So looking at the names, you may have a few guesses, like reduction meaning like you're reducing something, and then oxidation involving oxygen, but these names are very misleading. The names oxidation and reduction originated hundreds of years ago from people that really invented chemistry, but we would call them alchemists instead of chemists. These alchemists would melt down their metals to purify them. And they basically believed at that point in time that there was phlogiston, which would attach to substances and it would be driven away, or it would be kind of when you heated a metal, you would add phlogiston to it, or you would take the phlogiston out of it, and then as it kind of turned into its purest form, I'm not 100% sure on it. I'll link a video at some point about this, or we'll watch a clip in class that talks about it. Phlogiston is something very interesting, but like it's a dead science. It's not actually really useful to learn a ton about it. But basically, they thought that heating things would make them gain or lose phlogiston. It was basically what they thought. It was a particle that they thought was heat. Like heat was this particle thing. But Antoine Lavoisier, who is one of the fathers of modern chemistry, realized that this was actually due to this element called oxygen. That when you heated like a certain type of metal and you heated it up, you would have expected it to, as you heated it, you were adding phlogiston to it. You were increasing the amount of heat particles on it, so it would get heavier. But he actually noticed that a lot of the metals, while they purified them, would get lighter as they heated them. And he realized that it must be some kind of gas that was inside of it, and that gas he eventually named oxygen. This was literally how they discovered oxygen as a gas. It wasn't from us breathing it. It was from heating a bunch of metals. And because when heating it, if phlogiston was added, you would expect it to be heavier, but instead when you heated it, they got lighter. He determined that there was a gas that was being driven off by the heat, and that was oxygen. So in our example, this is really what's happening when you're purifying a metal oxide. In the case of literally iron 2 oxide, we've got 2 FeO, and you'll get 2 Fe's and O2 gas. So you'll get your iron metal, your pure iron metal, and you'll get an oxygen molecule driven off. And this is why it'd be lighter. For every 2 moles of FeO, you'll get 2 moles of oxygen or of iron, but this oxygen has been lost. So that's for every mole, that's 16 grams of oxygen that's just like pieced out of there. That's no longer a part of that experiment, or no longer a part of that metal. So that's why they would end up lighter, and then this oxygen would just drift away. It's no longer a solid, and both of these would be solids. So let's think about this in terms of electrons. And at first you might think, well, that seems really difficult. I don't know how I would do that. But really, if you just think of it as the opposite of what happened in NaCl. In NaCl, we had a metal and a gas that we combined together to make one solid. This is just the opposite of it. There, the metal lost electrons. And so here, because it's doing the opposite, because it's we had over here on the last one, Na and Cl were on the left side, and Na lost. Now we're splitting apart, which means the Fe, which is a metal in this reaction, must be gaining electrons. And that also must mean that the non-metal, in this case the oxygen, must have lost electrons. It must have, in this exchange when it bonded together, it must have lost electrons because the Cl gained them when we looked at the opposite. So really what we're doing here kind of for our first step is we figured out something that logically makes sense to us, hopefully. And again, we'll go in more detail about this in class if you have more questions. But Na and Cl together, when they are bonded, we can kind of logically see, oh, the Na lost an electron and went to the Cl, they ionically bonded. We're taking that's a little bit easier to wrap our head around and realizing that this is just the opposite. So we just flip what happened. Instead of the metal losing, it gains. Instead of the nonmetal gaining, it loses. If you haven't connected the frustrating dots then, you haven't realized that means that the term reduction in this case actually means gaining electrons. Whenever they were reducing, they were heating the metal and causing it to be reduced. The iron was reduced in that reaction. What was actually happening was the iron here gained electrons through the process of reduction. It was reduced. And that means that the oxygen was oxidized, which feels weird because that you wouldn't think it's like the whole water wet argument. So the naming doesn't really make sense. And the naming was there before they had discovered oxygen. However, scientists are stubborn. So by the time they realized that there was not actually this stuff going on, everyone was already calling it oxidation and reduction. And there's been a whole bunch of times where people have proposed changing the name to something that makes more sense. But chemists today still use oxidation and reduction, and there doesn't seem to be any changing of it. So our final definition here is that oxidation is a process where an atom loses electrons. The atom is then said to be oxidized. Reduction is a process where an atom gains electrons. That atom is said to be reduced. And again, in case it has to be made clear, and you need to make sure you know this, to have a redox, which is reduction oxidation, to have a redox reaction, they both must occur. This is a both or nothing deal. You cannot just have something oxidized because it must have gotten those electrons or sent those electrons somewhere, so that means something else must have been reduced. Okay, now on the flip side of that, oxidizing agents would be things that gain electrons in a redox reaction. That's because they helped in the process of oxidizing something. So back here, if something goes through oxidation, the other piece is an oxidizing agent. It helps that oxidizing happen. And a reducing agent is the thing that lost electrons in a redox reaction because it helped in the process of reducing. So if something is oxidized, that means it is a reducing agent. And if something is reduced, that means it is an oxidizing agent because it's which thing contributed to the other piece of the reaction. We give them both credit for helping the reaction occur. So let's look back at the equations that we were looking at earlier. The 2Na plus Cl2 gives 2NaCl, and the 2FeO gives 2Fe and O2. Starting with the first one, the sodium has lost electrons. That means it was oxidized. And that means it was the reducing agent because it helped the chlorine get reduced. The chlorine gained electrons, that means it was reduced, and that also means it was an oxidizing agent because the chlorine helped the sodium be oxidized. Again, it's weird to think that it is reduced, so it is an oxidizing agent, but you have to make sure you know the wording because questions could use those, swap back and forth between calling something either it went through this process or it is the agent of helping this process. If we go to the other one, 2FeO gives 2Fe plus O2. Oxygen has lost 2 electrons. That means it was oxidized. That means it was the reducing agent. Iron has gained electrons. That means it was reduced, which makes it the oxidizing agent. It's really, really weird. Now, there's a way to help you remember this that I think is in a later slide, but I'm going to go ahead and hit it for you right now if you want to add it to your notes. It's not on the screen anywhere. But the way that I remember this, or there's 2 ways you could remember this, I kind of use them interchangeably. There's Leo says Ger, Leo the lion says Ger, Leoger, losing electrons, oxidation, gaining electrons, reduction. Leo, Leo, Ger, Ger. Leo says Ger. Losing electrons, oxidation, gaining electron, reduction. The other way you can do it, it's the same type of technique, it's just a different set of letters, is oil rig. Oxidation is loss, OIL, oil. Rig, reduction is gain, RIG, rig. So oil rig or Leo says Ger. Either one of those is a way that you can help remember this. And then you can just remember that the agent is the opposite of whatever you figured out. So if you figured out something was oxidized, that means it was the opposite type of agent. It was a reducing agent. And if something was reduced, that means it was the opposite type of agent. It was an oxidizing agent. So this is kind of a lot to start with, but it'll get a little bit easier when we start doing some math and some logical stuff related to it. If you have any questions, please shoot me an email. In the meantime, though, this has been Mr. Diamond. Hope this first section doesn't scare you too much about advanced chemistry. Have a great rest of your day, everybody.